Hello, everybody. Hello, everybody. I'm Po-Shen Loh. Just first of all, I want to double check. Is everyone able to already see and hear what's going on? If you are, please send a message through the chat relay, and that's in the Zoom chat. You can do this on the YouTube. You can also chat too, but it's a little bit harder for us to see what you type there. Nevertheless, okay, if you can see and hear, this is fantastic. And so, first of all, let me introduce what this is all about. I'm Po-Shen Loh, and I'll be your host for tonight. I want to sincerely apologize for the delay. It's actually because I personally was setting up all of the technology, and we haven't used this particular site to stream for a while. I am a very, very, very proud MathCounts alumnus. And in fact, the reason why we really wanted to do this with MathCounts is because I'll just say for me, MathCounts is how I got my start. When I was doing all of these different things before, I found math in school and it was okay. But then when I found MathCounts, I said, my gosh, I don't know how to do these questions. And that's why it was so interesting. Today, I am a math professor at Carnegie Mellon, and I'm very, very pleased to not only work with students at Carnegie Mellon, but also to work with extraordinary people here on this live solve. Meanwhile, I just saw someone say, why are there echoes? Are there actually echoes, people? If there are echoes, please tell us in the chat relay, because then that means that there might be some issue. No. Okay, so I'm seeing a no echoes. In that case, that makes me happier. Let's keep on going. Yes, let me describe what this is about. So first of all, what is MathCounts? MathCounts is, I'd say, the biggest math tournament for middle school students in the entire United States of America. And it starts from the chapter competition. That's the local round. And then after that, the top students from the chapter competition go and represent their cities and their regions at the state competition. And then the top 4 people in every state go on to the national competition. And the chapter competition just finished up all of the rounds in February, and that's why we're able to discuss the problems today. The questions, by the way, in MathCounts are extremely, extremely interesting, as we'll see soon. But I want to introduce my other co-hosts here. And for each of them, what I'm going to do is I'm going to go in alphabetical order by first name as we introduce each of them. And for each of them, they'll also share what makes them feel special, what they feel is special about MathCounts 2 and how that also helped with their life. So I'd first like to introduce Akshay. Uh, Akshay, can you just wave? Well, not wave, say something, and it'll come through.
Yeah, hi everyone. I'm Akshay.
Wonderful. And Akshay is fantastic. So he's a high school sophomore. He's from Illinois, and he did MathCounts State. That means that, well, Illinois is quite the state. And so he was at the state competition in MathCounts for Illinois. He also has been doing math competitions ever since then as well, such as the Amy in high school. And he also plays tennis. But actually, maybe if you could share what you found so compelling about MathCounts, that'd be great too.
Yeah, so just like for you, math counts is really the start of competitions for me as well. And I feel like by doing math counts, I was able to meet a lot of other cool math people who I get to work with a ton now in high school at my school because my school has a lot of people who like doing these competitions. And I was able to make friends with a lot of them from the start through math counts.
Wonderful. Thank you, Akshay. We actually have 4 co-hosts today, so this is great. The next person I'd like to introduce is, let's see if I get my alphabetical right. It's Elena Baskakova. So Elena, could you say hello?
Hello, everyone. I'm Elena.
Wonderful. And so Elena's also been doing math competitions. She has actually coached math counts for 3 years as well. And so in high school, actually, she was doing the math Olympiads, and she actually did the USA Junior Math Olympiad and also went to MOP, which is how I got to meet her. MOP is the National Math Olympiad Training Program. That was in 2022. Of course, we like to say something fun about each person. She also likes the color yellow, but only when it's sunny. But meanwhile, Elena, would you like to share a bit about your feelings on MathCounts too?
Of course. Yeah, so there was definitely that sort of first engagement with some interesting types of math through math counts. But also in coaching math counts, I've got to see the problems from a new lens. I've gotten to see that they're actually really interestingly constructed and have a lot of theory behind them. And as well as looking at the types of problems there are in math counts. Math counts also gives me a way to foster a growing math community in my local community and really connect people with the power of really the math of love or love of math. Sorry.
Wonderful. Yeah, thank you, Elena. The next person I'd like to introduce is Evan Lim. Evan, could you say a hello?
Hello. Hello.
Yay! Okay, hopefully that showed on screen. So Evan actually has been doing lots of different competitions as well. In fact, in high school, he also took the USA Junior Math Olympiad, and he also did the physics. He also did the USA Physics Olympiad. But back in middle school, he was the Nevada State MathCounts champion. Fun facts. Well, Evan also likes bagels. This is something that I always remember. But Evan likes bagels. You never know if a bagel will show up on his screen, and he also likes 3D printing. Well, with that, I would like to introduce the last person that we're going to have doing the live solve today. And the last person is Jessie Wang.
Hello, I'm Jessie.
Hi, okay, fantastic. And Jessie was at MathCounts State in Texas. Texas is also quite the state. And she has also qualified for the USA Junior Math Olympiad as well. And she also likes watching hockey. So we have here a great crew of people. And so we're going to now switch over and start to do all of these MathCounts problems. And we're going to go in order. We're going to go in order 1, 2, 3, 4, and so on. My particular screen has question number 1 not so great. So I would prefer if maybe Akshay, would you like to run first? And then we'll just go run through order, 4 of you, and then me, and then we'll just keep going through.
Yeah, no problem. So let's start with problem number 1. I'm going to read it on my screen. It reads, what is the median of the following numbers? 529.14, 529.12, 529.13, 529.15, 529.16, and last but not least, 529.14. And express your answer as a decimal to the nearest 100th. So first of all, let's count. We have 6 numbers in total, so the median is going to be the average of the third and the fourth number. So let's sort these numbers from least to greatest. If we sort them, we're going to get 529.12, 529.13. We're going to have two 529.14s, and we don't even need to keep going because we want the average of the third and the fourth numbers. And this, because they're the exact same, is going to be 529.14. And we don't need to worry about expressing our answer as a decimal to the nearest 100th because this is already a decimal rounded to the nearest 100th. So let's check our answer. Amazing, and it's 529.14. Off to a good start.
Yay!
All right, then moving on to problem number 2. 2 lines are graphed on the coordinate grid shown. What are the coordinates of the intersection of the 2 lines? And express your answer as an ordered pair. Oh, well, luckily, I guess we're provided the coordinate grid already, so we can just kind of read it off the graph. So we can see that the x-coordinate, and remember for an ordered pair, we'll do x-coordinate then y-coordinate. The x-coordinate here, we can see here's 1 and there's 2. That lines up with the intersection point. And for the y-coordinate, we have 1, 2, 3, and it lines up with the 3. So our answer would be 2, 3. Now let's check. Indeed.
Awesome. Cool. And on to the third problem, moving right along. We want to find the absolute difference between -3 squared and -3, the quantity -3 squared. Well, 3 squared is, of course, 9. So -3 squared will be -9. And of course, when you square a negative number, you're going to get a positive number. The only difference is that, this one has the negative, this one doesn't. We're going to have +9. The absolute difference between 9 and -9 is 18. So our answer should be 18. Awesome. Yay.
Awesome. All right, moving into number 4. So we have if f of x is equal to 2 to the power of x plus 5, what is the value of f of 4? And so when it's asking for f of 4, all we have to do is plug in x equals 4. So in this case, we would get f of 4 is equal to 2 to the 4th plus 5. And so that's going to be 16 plus 5, which is 21. And yep, 21 is the right answer. Awesome.
Yay! Okay, so I think it's me now. I think I'm number 5. Let's see if this works. Okay, I have to read the question first. What is the perimeter of the square shown here with area 9 square centimeters? Oh, okay. I like 9. 9's a perfect square. What's 9? 9's 3 times 3. So that means that this should be 3 over here and 3 over there. And the only thing to be careful here is to make sure to read the question correctly. The question has the word perimeter. So the answer is not 3. The answer is 3 times 4, which I think is 12. Let's see if this is right. This is the sprint round, by the way. So the beginning questions are hopefully a bit faster. Yay! Back to you, Akshay.
Amazing. So it looks like we have 3b. So the question is, if 3b plus 12 plus 7 equals 5b plus 11, what is the value of b? So I guess we could just rearrange this equation, subtracting 3b on both sides, giving us 12 plus 7 equals 2b plus 11. And now we want to subtract 11 from both sides. So we get 12 plus 7 minus 11. Correct me if I'm wrong, but this is 8, and 8 equals 2b. So b equals 4. That's what the question's asking for. So we can circle 4 with confidence, and let's check our answer. It's 4.
Yay!
All right, moving into question 7. A heptadecagon. Ooh, I'm not sure I know what that shape is. 7, 10, 17? Ooh, okay, it tells me. 17-sided polygon. It's good that they tell me, I wouldn't have known. If a regular heptadecagon has perimeter 306 centimeters, what is its side length? Okay, well, we notice that there's this mention of regular in the problem statement. So what that means is that all of the sides of this figure are going to be the same. So if we call the sides something like S, then we'll know that 17 times that side length is equal to 306. So the problem just asks us to divide by 17 on both sides, or in other words, divide 306 by 17. Actually, we could divide this by long division, but I'm seeing a little bit of a shortcut, which is I recognize that this is actually 340 minus 34. And so 340 is 20 times 17. 34 is 2 times 17. So if we do, this is 17 times 20 minus 2, that gives us very quickly that the answer is 18 centimeters. Let's double check it. And 18 centimeters is the correct answer.
Awesome. Now, question 8. Vinny is ordering a 2-topping pizza, and the table shows the 3 choices of meat and the 5 choices of vegetable toppings offered. How many different combinations of one meat topping and 1 vegetable topping are there? Well, since there are 3 meats in the table, we have 3 options for our meat. And since there are 1, 2, 3, 4, 5 vegetable options in the table, there are 5 choices for our vegetable. So we simply take 3 times 5, or 15 options. 15. And that is correct. Huzzah!
All right, moving on into number 9. So number 9 is saying if the number 5 root 2 is the square root, so it's asking the number 5 root 2 is the square root of which positive integer? All right, so if we're saying 5 root 2 is the square root of a positive integer x, all we have to do is square both sides. And so if we square both sides, we get x on the right-hand side. And if we square 5 root 2, the square goes to both 5 and the square root of 2. And so 5 squared is going to be 25. Square root of 2 squared is 2. So that's going to give us 25 times 2, and that's going to give us 50. All right, let's check. Yeah, the answer is 50.
Yay! It's fun to work with such experts. Now it's supposed to be my turn. All right, Mr. Juarez can type 84 words per minute. How many words can Mr. Juarez type in 2 minutes and 30 seconds? So if I see 2 minutes and 30 seconds, I think of 2.5. So that's 2.5 minutes. And if I was supposed to do 2.5 multiplied by 84, it's easier not to multiply mixed numbers, but it's easier to multiply fractions. So let's go and flip the 2.5 into 5 divided by 2 times 84. Whenever you see something like this, don't multiply the top numbers first. It's actually better to divide first. That'll make it a little bit easier. So if I do this, then that cancels, and I get 42. So I need 5 times 42. Oh, there's a trick, by the way. When you multiply a number by 5, did you know that's the same as multiplying it by 10 and then dividing by 2? So specifically what this means is this is equal to, instead of 5, I want to call it 10 divided by 2 times 42. That's more convenient because I can cancel out the 2. That gives me 21. And so the answer is 210. And I wanted to say, of course, if you can do this in your mind, that's even better. But if you, I mean, I shouldn't say it's even better. If you do it in your mind, it's also convenient. But whenever I multiply by 5, I actually divide by 2 and then add a 0. Is this right? Yes. Akshay, on to you.
Amazing. So let's get rolling with question number 11. So this question reads, this year, there are 750 students enrolled at Blake Middle School. There's an increase of 25% compared to last year. How many students were enrolled at Blake Middle School last year? So it looks like we have a lot of parts of this question asking for how many students there were last year. So let's let a variable equal this. So let's let X be our answer, the number of students enrolled in this middle school last year. We know that there's an increase of 25%, meaning that this year there's going to be 5/4 of X, the number of students. And we set this equal to 750 because we're given that there's 750 students this year. So multiplying by 4/5 on both sides of the equation, we get 4/5 of 750 is 4 times 150, which is 600. And the answer is hopefully going to be 600. So let's check. Amazing. It's 600.
All right, on to problem number 12. If 5 zips equal 4 squawks and 3 squawks equal 5 bangs, how many zips equal 12 bangs? So this looks like it's a unit conversion type of problem, where our common currency between bangs and zips is the squawks. So I think the best course of action is to convert the zips or the bangs to squawks and then the squawks to zips. So let's start by taking those 12 bangs that we start out with. And the conversion rate to squawks is 3 squawks for every 5 bangs. So we can multiply this by 3 squawks to 5 bangs. And then that means that we now have, if we were to do this multiplication out, we would have our answer in squawks. But the next step is to convert squawks to zips. So every 4 squawks is equal to 5 zips. So we multiply this by the conversion factor, 5 zips, to 4 squawks. Now notice in this multiplication, all of our units cancel out except for the zips. That means that we're going to get our answer with the correct unit. So that's how we know that we're doing the conversions correctly. So now all that's left is we just have to multiply these numbers out. So on the top, we have 12 times 3 times 5. And on the bottom, we have 5 times 4. So we can cancel the 5s and we can cancel the 4 with the 12 to be left with 3. So our answer should be 9 zips. Let's double check that. And that's correct.
Nicely done. Now we have question 13, a triangle. And we know that the degree measures of the angles of this triangle are x, 3x minus 10, and x minus 10 degrees. And we want to find the degree measure of the largest angle. Well, I think the thing to do here is to solve for x by, adding up the angles and using the fact that these angles must add to 180 degrees because we have a triangle. So x plus x minus 10 plus 3x minus 10 equals 180 degrees, which means that 5x minus 20 equals 180 degrees. 5x minus 20 equals 180 degrees. And adding 20 to both sides gives us 5x equals 200 degrees. 5x equals 200 degrees. So x equals 40 degrees. And from this, we can pretty quickly calculate all of the angles. X here, well, that's 40. X minus 10 is 30. And 3x minus 10 is 120 minus 10, which is 110. Of course, we really didn't need to calculate x minus 10 because obviously that will be smaller than x. But either way, we end up with 110 degrees. And yay, that's correct.
Great. All right. So we're moving on to number 14 now. So number 14 says Tiffany is a stylist at a salon that specializes in hair braiding. It takes Tiffany 15 minutes to complete 2 rows of box braids, and at this rate, how many hours will it take Tiffany to complete a hairstyle that consists of 42 rows of box braids? Okay, that is a lot of rows. That is a lot of rows of box braids. So it tells us that it takes Tiffany 15 minutes to complete 2 rows. And so since it wants our answer in hours, it might be easier to convert everything to hours first. And so 15 minutes, since there are 60 minutes in an hour, if we multiply by 60 minutes in 1 hour, we see that 15 minutes is actually 1/4 of an hour. So now we know for 2 rows, it takes 1/4 of an hour. So we have 2 rows, 1/4 hour. All right, and so now we want 42 rows of box braids. So if we're going from 2 rows to 42 rows over here, we're actually multiplying by a factor of 21 because 2 times 21 will give us 42. And so if we're multiplying by 21 over here on the left, we also have to multiply by 21 on the right. And so we're going to multiply by 21 over here. And so we end up with 1/4 times 21. And so 1/4 of an hour times 21 of those iterations is going to give us, I'd say 5 1/4. So 5 1/4 hours to finish that hairstyle. And yep, that is going to be the right answer.
Yay! Okay, let's go on. The area of a rectangle is 24 square inches. If the length of the rectangle is 1.5 times the width, what is the rectangle's perimeter? Whenever I see things like 1.5, I prefer to think of fractions. So 1.5 to me is 3/2. So let's see if I can do this. Oh, you know what? I'm just thinking out loud. I might want to not even write fractions. So here's what I'm going to do. I'm going to put an x in, and I'm actually going to write that the width is 2x and the length is 3x. That's because the ratio of the length divided by the width is going to be 3 divided by 2, so I can do this. Now, this might make it easier because if I just want to find the perimeter, well, I just need to take the 2x plus 3x and then double that. But I can use the area part. 2x times 3x is 6x squared, and that's 24. So that means that x squared is equal to 4. So what's x? -2. Just kidding. X is 2. Well, I mean, -2 is also possible, except that wouldn't be a very good rectangle. So I'll use x equals to 2. And then the next thing I'll do is I need to know what's the perimeter. Okay, perimeter. Perimeter will be 2x plus 3x and then double that. So that's 10x, which should be 20. Let's see if it's 20 or -20. It's 20. All right, on to Akshay.
Amazing. So let's read this problem. The product of 2 integers is 36. What is the greatest difference the 2 numbers could have? So there's really 2 cases here. Either both the numbers are positive or both of the numbers are negative. Let's see if that even matters. So in the case that both numbers are positive, we want one number to be as small as possible and the other number to be as big as possible. The smallest possible divisor we can have is 1, and the largest possible divisor is obviously 36, and thankfully 1 times 36 is 36. So this gives us a difference of 35, and that's the best we can do in the positive case. If we test out the negative case, it seems like it won't even really matter because the smallest number we can have is -36, and the largest positive number we could have, largest negative number we can have is -1. And if we take the difference, we're again going to get 35. So we didn't really need to worry about the positive and negative cases in the first place, and we can circle 35 with confidence, and let's check this. Yeah, the answer is 35. Amazing.
Moving swiftly on to problem, is it 17 already? Wow, okay. On to problem 17. A positive integer less than 100 has fewer than 6 positive integers. What is the greatest possible value of this integer? Okay, I think the plan of action here is to start at 99 and go down. because either I will get something that has less than 6 positive integers somewhere, or I will stop at 97, because 97 is a prime number. That only has 2 factors. So I'll know that if it's not 99 and not 98, it has to be 97. So we can just check 99 and 98. So 99 is equal to 9 by 11, or 3 squared by 11 to the first. And to find the number of factors in total, what we do is we take this 2 and we add a little 1 to it, and this 1 and we add 1 to it as well, and then we multiply these two quantities. So in this case, the number of factors would be 3 times 2 is equal to 6. But we're looking for strictly fewer than 6 positive factors, so that one doesn't work. How about 98? Well, 98 is actually pretty similar to 99 in that it's equal to 7 squared times 2. And you'll notice that when we had a square times a prime number, that gave us 6 factors. So in this case, even though the prime number is different and the squared number is different, we're still going to have the same number of factors. This also gives us 6 factors. So that means that we're down to 97, which is a prime number, and therefore our answer is 97. And that it is.
Awesome. We have, oh, I get a second problem about triangles. That is fun. Well, we have a right triangle with one leg measuring 8 centimeters that has an area of 24 centimeters. If the lengths of the legs are both increased by 2 centimeters, what is the area of the resulting right triangle? Well, the area of a right triangle is going to be the product of the 2 legs divided by 2. So I know if I draw our original triangle, one side will be 8 and the other side will be 6, since 8 times 6 over 2 is 24. Alrighty, increasing the lengths of both legs by 2, well, the area just ends up being 10 times 8 over 2, which is 10 times 4, or 40. Area of 40. Let's see. Yay, 40 centimeters squared.
Awesome. All right, moving into number 19. So this is a really long problem, so I've slightly compressed the problem vertically, but I'll read it out. So number 19 says, Mrs. Keaton emptied bags of candy into a bowl before the math club meeting. At the beginning of this meeting, the club members in attendance each took 2 pieces of candy from the bowl. During the meeting, Mrs. Keaton found another bag of candy and added those 17 pieces of candy to the bowl. At the end of the meeting, each club member except the one who left the meeting early took 1 additional piece of candy from the bowl. If there were 27 pieces of candy left in the bowl after the meeting, and there were twice as many pieces of candy in the bowl before the meeting, how many club members attended the meeting? All right. So let's start with what we know first, right? So the problem is saying there's 27 pieces of candy left in the bowl after the meeting. So we know we end with 27, and it tells us there were twice as many pieces of candy in the bowl before the meeting. So that means we started with 54, right? 2 times 27 is 54. So if we start with 54 and we end with 27 pieces, that means we lost 27 pieces throughout the meeting. And so what I'm going to do is I'm going to say we lost 27 pieces of candy, right? And so we're going to represent this loss of 27 pieces of candy. And so what I'm going to say is we don't know how many club members we have, so I'm just going to call it a variable x. And so rereading the problem, it tells us at the beginning of the meeting, the club members in attendance each took 2 pieces of candy. So if x is the number of members, then there were 2x pieces of candy taken from the bowl. During the meeting, it tells us she found 17 more pieces of candy, and so that means we added 17 to the number of candy in the bowl. And then finally, it tells us at the end of the meeting, every single club member is going to take 1 piece of candy, except for the last member that left. And so we're going to be subtracting pieces of candy. And although we do have x members, we only have x minus 1 members taking candy because it tells us 1 left early. So we subtract x minus 1 pieces of candy. And that should give us a deduction of 27 pieces of candy. Okay, let's go ahead and solve this one. And by the way, the signs are just for keeping track of when candy was added and when it was lost. So when we took away candy, I used negative signs. When we added it, I used addition. Okay, so this is going to be negative 27. If we expand out this minus x plus 1, that gives us plus x. No, that gives us minus x plus 1. So this is going to give us negative 3x. and plus 17 plus 1, that's going to be plus 18. And so we can move some things to the other side. We get 3x is equal to 27 plus 18, which is 45. And so that's going to give us x is equal to 15 members. All right. And yeah, that's going to be correct.
Yay! Okay, that's good. I'm glad you got that question, Jesse, because I don't have the ability to compress. So hopefully my question, oh boy, what's this? Well, I can get out of the way. That's what I can do. What is the value of the expression shown? Express your answer as a common fraction. Okay, so whenever you see a big fraction, you have to just start from the bottom and move on up. And oftentimes I would like to write on the actual paper where I have it. Oh, well, I guess I can write on the screen. So if I have 5 over 1 plus 7, so this part is 5/8. Okay, so that part's 5 over 8. And then, oh, this question's cool. I bet the answer is Fibonacci. All right, let's see what happens, because this is actually a famous kind of question. See, if I take 1 plus 5/8, or maybe it's not Fibonacci. No, it's not Fibonacci. There's like random other stuff. Okay, never mind. I got all excited because sometimes when I see numbers like 5, 8, and 1, because 1 plus 5/8, this would give you the denominator, not denominator, but this part down here would be 13 over 8. Okay, so if that's 13 over 8, all right, it's not quite Fibonacci. If I had wanted it to be Fibonacci, I would have needed to have different numbers on top. But okay, so the bottom part is 13 over 8. And so now I'm going to do 1 plus, let's do this part. This part would be 1 plus 3 divided by that, which is 1 plus 3 divided by that is 3 times 8 is 24 divided by 13. So that's equal to 13 plus 24 is, I think it's 37 over 13. Arithmetic is actually quite hard for me. So let's see. So if that's true, I go one more level up. If I go one more level up, let's see, do I have another screen with the thing? Yes, I do. Good. So I know that the part with the 3, up to the 3, this is 37 over 13. Okay. And then I'm going to keep on going. So if that's 37 over 13, well, when I invert that, when I flip it over, then this part would be 1 plus 26 over 13. No, 26 over 37. Okay. And that's equal to 37 plus 26, 63 over 37. Is that right? I have to look at this slowly. 7 plus 6 is 13. Seems okay. And then I have to flip it over. I want to make sure this is reduced form, but this is reduced form because 37 is a prime. So when I flip the whole thing over, I would get 37 over 63. Let's see. I don't know if I got it correct or not. I often will make arithmetic mistakes, but I guess I'm okay. Thank goodness.
All right. Seems like we've been crushing the first 20 problems, so let's see if we can do the same for problem number 21, which reads, the product of 3 consecutive multiples of 5 is 42,000. What is the least of the 3 multiples? So they're multiples of 5, so we can represent it as 5 times some variable. So let's represent the numbers as 5 times x minus 1, 5 times x, and 5 times x plus 1, because these are consecutive multiples of 5. Notice that this number is 5 more than this, and the third number is 5 more than the second number. And we multiply them and we get 42,000. So let's write that down. 5 times x minus 1 times 5x times 5 times x plus 1 equals 42,000. It seems like we have 3 5s here and they multiply to 125. So let's divide by 125 on both sides. It seems like 125 times 8 is 1,000. So 42,000 divided by 125 is 42 times 8, and 42 times 8 is 336. So x minus 1 times x plus 1 equals 336. And this is we could obviously do this problem algebraically, but this number 336 seems pretty small, so let's just guess around. If we guess, so to start off, we notice that 6 cubed is a little bit less than 336. 7 cubed is a little bit more than 336. So it's somewhere around that 6, 7, 8 range. So if we try x equals 6, we get 5 times 6 times 7 And that's definitely not going to equal 336. But if we try x equals 7, we're going to get 6 times 7 times 8. And 6 times 7 is 42. 42 times 8 is 336. So x is 7. But the question asks for the least of the multiples. So we want to find the one where x equals 6 because that's the smallest x in or 3. I guess that's the smallest number we're multiplying by 5 by. So we get 5 times 6 equals 30, which is hopefully the answer. So let's check. Amazing, it's 30.
Great. Continuing on with question 22. Alva adds up all the positive integers less than 2023, and Beth adds up all the even positive integers less than 2023. What is the remainder between when the absolute difference between Alva's and Beth's sums is divided by 1,000? Okay, wait. So Alva adds up all the positive integers and Beth adds up all of the even positive integers. So if we subtract those, we're just going to be adding up all of the odd positive integers between 1 and 2023. Oh, less than 2023, but equalish to 1. Okay, so from 0 to 2022, I guess, but all the odd numbers. So okay, well, there's actually a pattern when you add up odd numbers. So notice how 1 is equal to 1 squared. But when you do 1 plus 3, that's equal to 4, you get 2 squared. And if you add a 5 to this, that's equal to 3 squared. And actually, you can like draw this out in a little picture if you want. This is like 1, and then when you add 3, you make it into a 2 by 2 square, and then when you add 5, you make it into a 3 by 3 square, etc., etc. But it turns out that when you add together odd numbers, you'll be able to get squares. And these squares are perfectly increasing in value, right? We started with 1 squared, we went to 2 squared, we went to 3 squared, etc. And how did this happen? Well, the first number corresponded to 1, the second number corresponded to 2. So what we want to find is the last number we're adding is 2021. We want to find which odd number this is in the progression. So notice how 1 corresponded to 1, but 3 corresponded to 2. So actually what we're doing is we're taking, if n is the odd positive integer, the place it is in the sequence is n plus 1 over 2. We can double check this by 1. If we plug in 1, we should get 1. And we do, and if we plug in 3, we get 4 over 2 is 2. So this is how we find the place of the number in the sequence. And if we were to plug in 2021, we'd get 2022 over 2, or 1011. Now we need to square it, and then find the remainder when divided by 1,000. Now squaring this seems like a lot of work. What if we find the remainder first, and then square it? Now, why is this valid? Well, just like quickly decomposing this, because sometimes this doesn't work. Like you can't find the remainder first. But here is 1,000 plus 11. And if we were to square this, we would get 1,000 squared plus 2 times 11 times 1,000 plus 11 squared. So you can see that when we expand it, everything has a factor of 1,000 except for 11 squared. So that's why this works. But in this case, we just take 11. We take the square of this, 11 squared. That gives us 121. Let's just double check that this is what the question's asking for. So we found the absolute difference between the sums because we added together all of the odd numbers in the sequence. And then we found the value of this sum by finding the place that the last number is in the sequence, and then we took the remainder, mod 1000, and we squared it to get 121. Now let's check that that is the answer. And it is.
That's fun. I really like that squaring and remainder trick. And speaking of squares, we have something that's sort of a square. It's a hexagon. Aaron draws a regular hexagon. Then Becca's like, nah, I can do you one better, and draws a regular hexagon connecting all of the midpoints of the sides of, well, Aaron's hexagon. And we want to find the ratio of the area of Becca's hexagon to the ratio of the area of Aaron's hexagon. And one thing I'll note is that sometimes in these problems, I'll forget which one I'm finding the ratio from and which one I'm finding the ratio to. So when I get an answer, I want it to be less than 1 because this hexagon in the middle is smaller than this hexagon on the outside. Just a small note. Okay, and the nice thing about area is that it scales in nice ways. So I can just find the ratio of the side lengths of these two hexagons, and I'll be good. If I square the ratio of the side lengths of these two hexagons, I'll get the ratio of their areas. So for that, I'm going to focus in on this little triangle here, because it provides a really convenient way to relate both the side of Becca's hexagon, rather half the side of Becca's hexagon, to half the side of Aaron's hexagon. Yes, I have bad short-term memory for names, but that's okay. Hexagon A has half a side here, and hexagon B has half a side here. And moreover, the nice thing is I don't care about what the actual side length is. I just care about the ratio, which I can very easily find by doing some angle stuff. So the interior angle of a hexagon is 120 degrees, which means that this green angle here is going to be 60 degrees, 60 degrees. And so the little red triangle, the little red right triangle rather, that I've drawn here is going to be a 30, 60, 90 right triangle, which means that, I don't know, I can set this length here to be √3, this little length here to be 1, and the hypotenuse, which is half the side of Aaron's triangle, to be 2. And I will get a correct scaling. And so the ratio of the sides of Aaron's hexagon to Becca's hexagon is √3 divided by 2. And how do I go from the ratio of the sides to the ratio of the area? Well, I square it. It's the same as going from centimeters to square centimeters, that sort of thing. And √3/2 squared, well, that's just 3 divided by 4. And for a sanity check, it is good that this is less than 1, because again, Becca's hexagon is going to be smaller than Aaron's hexagon. So yeah, 3/4 is our answer. And that's right. Yay.
Awesome. All right. So moving on into number 24. So number 24 says, at a certain MathCounts chapter competition, the top 6 mathletes score on the sprint round were 23, 24, 26, 28, 28, and 29. Those same mathlete scores on the target round were 10, 10, 12, 12, 14, and 16, but not necessarily in the same order. First place is awarded to the mathlete with the highest combined sprint and target round scores. So what is the least possible score for the first place mathlete? Okay, so these numbers are actually pretty big. So I see what it wants, right? It wants us to make combinations sort of match these numbers up, match a sprint to a target score, add them up, and find the least possible value for first place. So these are big numbers. So what I'm actually going to do is I'm going to scale all the sprint and target scores down a little bit, just so they're easy to work with. So I'm going to scale every single sprint score down by 20. So my new numbers are going to be 3, 4, 6, 2 8s, and then a 9. And so for the target round, I'm going to scale them all down by 10. So I'm going to have 2 0s, I'm going to have 2 2s, a 4, and a 6. And so all this means is that when I find a sum with these numbers, I just have to add back the 20 plus the 10 to get the least possible score for the first place mathlete. So I'm just going to put plus 30 right here, just so I don't forget to add that to my final answer. Okay, so all I have to do is just make combinations with this now. So to start, I'm going to try to estimate where the average of all these numbers are. We know we need to combine every single sprint to a target score. So if I find the average, I know at least a number I should shoot for almost. Because we know the first place has to have a score that's at least above the average score. And so if I add all these numbers up, if I add up all the sprint numbers, I get 3 plus 4 plus 6 is 13. 13 plus 16 is 29. 29 plus 9 is 38. And then if I add up all the target scores, I get 4 plus 4 plus 6, that's 14. And so if I add this up, I should get 52. And because there's 6 mathletes, 52 over 6, it's a little more than 8. So I know the first place winner is going to have a score that's higher than 8 using the scaled system of scores. So what I'm going to do is I'm going to look for 9. So if we can find a possible combination where the largest combined sum is 9, then we know that's going to be our minimal answer. So if we want a 9, we can try using 9 and 0. So I can try connecting these numbers. And so with our 8, I'd have to connect it with the 0 to make it smaller, but then there isn't something to do with the other 8. And so that isn't going to work. If we try to find a 9 with the 3 and the 6, we know this 9 has to connect with the 0, but then we would have a tie for first place. And we don't really want a tie for first place. So I don't think 9 is going to work as a combination. There's really no other way to take a number from here and a number from down here and get a 9. So I'm going to start looking for 10. Okay, so if I want to make a 10, I can't use the 9 to make a 10, but I can use the 8 to make a 10. So I can connect a 2 and an 8 to give me 10. And so everything under that, everything has to be smaller than 10. So with the 9, that means I have to connect it with a 0 to make that sum smaller than 10. So I have a 9 and a 0. That means with the next 8 I have, that also has to connect with a 0 because 8 plus 2 would be another 10. And that would be a first place tie. So I have this so far. What can we do with the 6? Well, I can't put the 6 with anything bigger than the 4, but I can put it with a 2. So if I connect the 6 with the 2, that gives me an 8. And then I can just connect the 4 with the 4. And then it might be a little hard to see, but I'm going to connect the 3 and the 6 down here. Oh, that's going to give me a 9. Let me see if there's a better way to do this. So with a 10, I have a 2 and an 8. I have a 9 and a 0 and an 8 and a 0. I guess I have to connect 6 with 2. And so I get, oh wait, no, that does work because I do have a 9 that's less than 10. So I can just connect the 2 4s to give me an 8, and I can connect the 3 and the 6 to give me a 9. So that means my largest sum is going to be this right here, the 8 and the 2. So that's going to be a 10. And so our smallest first place sum is going to be a 10. So I'm going to add that to the 30, and that's going to give me 40. So that's the least possible score for the first place mathlete. And yeah, that is going to be the right answer.
Wow, that was pretty good. I actually will say I myself would have just tried to connect things together and hope that I got the best answer, but I like your averaging and the inequality thing. That was pretty clever because you actually proved that it has to be 39 or higher. Because sometimes when you do these questions, you're not really sure. It's like, is that really the best answer? So well done. Well done. Okay, let's see what I've got. Okay, this question. In the figure shown, got some parallel lines. Given the indicated angle measures, what is the value of t? Okay. I'm going to move to the next screen. Yes, I've got this. So now it's maybe a bit more visible for everyone. I'm going to use, first of all, I like everything to be in one triangle. So I see that there's a 6t minus 6, which I can put here. This is 6t minus 6. And then now up here, I have this situation where there's 2 of these angles, and then there's 1 more of these out here. And it's very nice that if I take these 2 angles and I add up, if I add this little one over here, I'm supposed to get 180. But that's the same as 180 is also achieved by that other one adding this one. So what that means is that the 2 remote interior angles add up to the same as the exterior angle. So I guess we can solve an equation now. Just to double check, we need to find t. So I have 6t minus 6 plus this 11t minus 1 is supposed to be 16t plus 1. So let's add them together. 6t minus 6 is 17t minus 7. That's supposed to be equal to 16t plus 1. So that means that t is equal to 8. Okay, I'm just doing a quick sanity check to make sure that there are no negative numbers, but it looks okay, no negative numbers, so hopefully that's the answer. T is 8. Yay! I'm going quickly, by the way, because people were asking when this ends. We actually were planning to stay here until half an hour after the hour, so that's a total of 90 minutes. So we're going to continue powering on through to see how far we can get. Maybe we'll even get to do some of the target round questions. With that, Akshay is up next.
Yeah, so let's jump through problem number 26. This question reads, what is the sum of all positive solutions to x minus 1 times x squared plus x minus 2 times x squared minus 5x plus 6, which is supposed to equal 12 times x squared minus 4x plus 3 times x plus 2. So first of all, positive solutions is super important. We don't want any negative solutions, so I'm going to underline that. And let's get moving with this question. I see some factorable polynomials here, so let's factor them. So on the left-hand side, we're going to keep the x minus 1 as x minus 1. The x squared plus x minus 2 can be factored as x plus 2 times x minus 1, and the x squared minus 5x plus 6 can be factored as x minus 2 times x minus 3. Amazing. And this is going to equal the right-hand side, which is 12 times x squared minus 4x plus 3, which is x minus 3 times x minus 1. And x plus 2. We have the x plus 2 left over. So I'm just going to check this factoring real quick. All right, seems good. So let's jump forward to this question. We want the sum of all positive solutions, so -2 definitely doesn't work. So we're not going to include that. And if this whole expression equals 0, the left-hand side is 0 and the right-hand side is 0, we definitely have a solution. So let's first look for those before we divide anything out, because if we divide x minus 1, for instance, on both sides of the equation, we are going to lose some solutions. So before we divide anything out that can cancel, let's find the solutions that make everything 0. So 1 is a solution because x minus 1 is on this side, and x minus 1 is on this side. And 2 is not going to be a solution because it's not on the right-hand side. 3 looks like it's going to be a solution because there's x minus 3 on the left-hand side and right-hand side. So we have 1 and 3, and that seems to be it. So we have 1 and 3 so far. Let's see if we can find any more by dividing stuff out. So we can cancel this x minus 1 on the left-hand side with the x minus 1 on the right-hand side. We can cancel the x minus 3 on the left-hand side with the x minus 3 on the right-hand side. And we can cancel our x plus 2's out as well. And we land with x minus 1 times x minus 2 equals 12. Expanding the left-hand side, we get x squared minus 3x plus 2 equals 12. Subtracting 12 on both sides, we get x squared minus 3x minus 10 equals 0. And factoring this, we get x minus 5 times x plus 2 equals 0. So x plus 2 again gives us a negative solution of -2, which we don't want, but we do take this x minus 5 solution of 5. And it seems like these are only solutions. We add 1, 3, and 5, and we get 9. So this was a super fun problem. Let's see if we got this correct. And it's 9. Amazing.
Great. Moving on to the next problem. Edward has a meeting at 4 p.m. He leaves his house at a random time between 3 and 3:30, and it takes him a random length of time between 30 and 45 minutes to get to the meeting from his house. What is the probability that Edward arrives early? Okay, so since there's a lot of continuous stuff going on here, like we don't have discrete intervals of time, we have continuous time, what I'm thinking is we should plot this as a geometric diagram and find the geometric probability. So in short, what we're going to do is we're going to plot out all of the possible times that he can arrive. This is going to, or yeah, all of the possible spans of time that he can arrive. This will form some solid region in a 2D plane. And that we can find the area of that, and we can also find the part of that that is before 4 o'clock. Okay, so it seems like let's draw the axes here. So, ooh, that's a wiggly axis. So this horizontal axis will represent, or the x-coordinate will represent the time he leaves, and the y-coordinate will represent the times that he can get there. So, for example, so we'll have that this origin is 3, and then we will have 330 on the horizontal axis. And then on the vertical axis, we'll have 330, 4, and the latest he can arrive is 4:15, right? So if he leaves at 3, then the earliest he can arrive is 3:30 because it takes him at least 30 minutes to get there. And the latest he can arrive is 3:45, right? Because it takes at most 45 minutes to get there. Now, if we were to increase the departure time by 1 minute, we would shift this segment up by 1, right? Because it's still, the lower bound is still 30, the upper bound is still 45. So actually, each time we shift over by 1 minute, we'll shift up by the same amount. So what this means is we can draw a line with slope 1 that represents the lower bound, and a similar line with slope 1, 15 minutes higher, that represents the upper bound. And we can see where this intersects the 3:30. This is the latest possible departure time. And that would mean that he arrives at 4 o'clock at the earliest. And at the latest, he arrives at 4:15. And if we connect these two line segments, we'll see that the slope is actually 1, right? Like we go over 30 minutes, we go up 30 minutes. So this is the region, this orange region, is all possible times that he can arrive. We're looking for everything under 4 o'clock. So if we were to draw this line here that represents 4 o'clock, and it intersects at this vertex, we want everything below this region. Now, something really nice here is there's a lot of symmetry. So actually we could go and find the areas, but we don't need to, because look here, this horizontal line intersects this tilted line at the midpoint. So we can draw this middle line here that divides the figure into 2 equal areas. And similarly, this top area is symmetric about this horizontal line. So in effect, this top portion is 1/4 of the entire figure. You can see if you also draw this bottom line, you can see that this pink line splits everything into 4 identical triangles. So the chance that he arrives too late is 1/4, but what we're looking for is the chance that he arrives early. And it asks for a common fraction, so in this case, the answer would be 3/4. As it is.
Awesome. And now we're on the third to last question of the sprint round. What is the least 9-digit positive integer that contains each of the digits from 1 to 9 exactly once and is divisible by 99? Okay, well, I'll just start by noting that the least 9-digit positive integer containing all these digits is, of course, going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. But since this is question 28, I'd be willing to bet a good deal that this is not divisible by 11. However, it is divisible by 9. And that's because the sum of 1 plus 2 plus 3 plus 4 plus 5, etc. to 99, to 9 is going to be 45. And there's a divisibility trick that says if the sum of the digits is divisible by 9, then the number itself is going to be divisible by 9. So no matter how we rearrange these digits, we're still going to get something divisible by 9. Now, there's also an especially useful divisibility trick for divisibility by 11. And this comes from the fact that 10 is 1 less than 11. So 10 effectively leaves a remainder of -1 when divided by 11, which is to say that if we're trying to find whether a number is divisible by 11, we should take the alternating plus minus of every single digit. So for example, 45 or 456,123, well, is this divisible by 11? We'd take 4 minus 5 plus 6 minus 1 plus 2 minus 3. Or alternatively, another way to phrase this is 4 plus 6 plus 2 minus 5 plus 1 plus 3. In this case, that is 12 minus 9, which is 3, which is not divisible by 11. So this number is not divisible by 11. But this alternating digit sum is also how we can extend our idea to the 9-digit number, because if we have 9 digits, then we're going to be taking the sum of the first, third, fifth, seventh, and ninth digit and subtracting the sum of the second, fourth, sixth, and eighth digit. And hopefully that's a multiple of 11. Alrighty. In other words, we need to find two numbers that add up to 45, because remember, all of these are digits, and all in all, they will add up to 45. So we need to find an A for the sum of these digits and a B for the sum of these digits that, well, we know they add up to 45. And A minus B needs to be divisible by 11. Or another way to put this is A minus B equals 11, 22, 33, 44, etc. Something like this. And let's see if we can find some numbers like this. What if A minus B equals 11? Then we have something plus 11 is 45. Specifically, B plus 11 is 45. So 2B equals 34, which means B equals 17. So I'll write that down. If A minus B is 11, then one of our sums will be 17, and the other of our sums will be 28. Okay, what if A minus B is 22? Well, then we'd have B plus 22 equals 45. But if you think about it, this gives us a non-integer for B, because 22 is even, 45 is odd. We're going to get an odd number, and we can't divide an odd number by 2. Moreover, B has to be, if we go further and try the 33 case, where you get B plus 33 is 45. Well, we're able to take this subtraction and get an integer value of B. We get B equals 12, or sorry, B equals 6, 12 over 2. Perhaps I shouldn't have skipped that step in my head. But this means that the other digits need to have a sum of 45 minus 6, or 39. What's the largest possible digit sum we can have? Well, is this even possible? This is not, because if we make B equal to 9, then one of the digits here has to be a 1, the next will be a 2, the next will be a 3, the next will be a 4. But this sum is already bigger than 6. In other words, from this work, we know that 5 of our digits have to add up to 28, and 4 of them have to add up to 17. Cool. Let's find some digits that add up to 17 and 28. And what we want to keep in mind is that we care a lot about making this number as small as possible. So in reality, there are a lot of options for the numbers that could add up to 17, or the numbers that could add up to 28. But we probably want to restrain ourselves by putting 1, 2, 3 in the front. And what if we continue 1, 2, 3, 4, 5, 6, like this? Well, then our running sum for the odd place digits is now 1 plus 3 plus 5, which is 9. And our running sum for the even place digits, 1 plus 3 plus 5, which is 9. And our running sum for the even place digits is 12. Cool. And we have one last digit that contributes to the even spot. And this digit has to be 17 minus 12, which is 5. That's impossible because we already used up our 5, which means that 5, 6 is not an option. So what's the next best we can do? The next best we can do would be putting a 6 here. Does this work? Well, if we put a 6 there, the sum in the odd places is 6 plus the next digit here, and the sum in the even places right now is 1 plus 3, which is 4, and 6, which makes 10. Okay. And so Oh, we have actually 2 more digits that can go in this spot. So this is not the most useful, but the smallest number we can make using this would have a 5 in this spot. Oh yeah, and this doesn't work because 2 plus 4 plus 5 is 11, which, requires us to have a 6 in this spot. Or perhaps to clarify, we need the sum of this digit, this digit, this digit, and this digit to be 17. The sum of these 2 digits here is 6. So the sum of these 2 digits needs to be 11. But you can't make 11 out of all the remaining digits we have. It is impossible. Cool. So yeah, 6, 5 is impossible. We cannot have, or more precisely, having 6 after the 4 is impossible. So unfortunately, the best we can now do is 7. And we should see if 7 works. Well, now the running sum in the even digits is going to be 2 plus 4, which is 6. So again, the remaining digits need to add up to 11. Well, is 11 possible? What are our remaining digits? Our remaining digits are 5, 6, 8, and 9. And we can make 11 with 5 and 6. So let's just put 5 here and 6 here, because, well, that is going to make a smaller number than if 6 were here and 5 were here. Okay, and of course, 8 and 9 add up to 17, and combined with the 1, the 3, and the 7, they'll add up to 28. So the best we can do is putting 8 in the third to last spot and 9 in the last spot. And so by process of elimination, well, we happen to be lucky enough that 1, 2, 3 yields something that works. And then we found that there could be no digit here less than 7. And when we put 7 there, the smallest number we could possibly get is 123,475,869. Alrighty. And that is correct. Whew.
That was a long problem. All right, on to number 29. I really doubt this one is going to be much shorter. So this one says Stephanie rolls 3 standard dice. What is the probability that the product of the 3 numbers she rolled is not a multiple of 8? Express your answer as a common fraction. All right, so with this one, if we're rolling a standard dice, that means we have a choice between the numbers 1, 2, 3, 4, 5, and 6. And so when something is a multiple of 8, that means when we write its prime factorization, if we look at the number in the exponent of 2, that means if we write this number as 2 to the something times a bunch of other factors, this exponent is at least 3 if it's a multiple of 8. So it can be divided by 8. So in other words, if we look at all of our numbers, we know that 1 contributes 2 to the power of 0, 2 contributes a factor of 1, 2, 3 is odd, so it doesn't have any factors of 2, 4 has 2 factors of 2, 5 has none, and 6 contributes 1 factor of 2. So really what this is asking is if we're trying to find a number that isn't a multiple of 8, that means when we multiply the numbers, the exponents are going to add up to something that's less than 3, so 0, 1, or 2. So with this one, we're probably going to have to dive into some casework because it does mean that ordering is going to matter, right? So we have a lot of different options. I guess we'll just start with 2 to the power of 0, 2 to the power of 1, and 2 to the power of 2. And so we don't really care about all the other factors. That's why I didn't write the times 3 over here. We're just going to pay attention to factors of 2. Okay, so if our product ends up with no factors of 2, that means we picked either 1, 3, or 5. And so if we picked 1, 3, or 5, in terms of order, that means we have 3 choices for every single of the 3 numbers that she could have rolled. And so that gives us 3 to the power of 3, which is 27 cases right here. So there are 27 different cases where the product could end up with no factors of 2. Okay, so now 2 to the power of 1. That means our product is going to have 1 factor of 2. And so that means the number that is going to contribute that power of 2 is going to either be 2 over here or it's going to be 6. And then that means the other 2 numbers is either 1, 3, or 5. It's one of the odd numbers. So we're going to have to dive into a little bit of casework here, it seems. But the way we get 1 is going to be 1 plus 0 plus 0 in terms of the exponents. All right, so for the number that's going to contribute 1, we have two choices. We can either pick 2 or we can pick 6. So that's going to be two choices right there. And so depending on if these two numbers are the same, the numbers that contribute powers of 2, we're going to have different number of cases. And so let's say the first case is the numbers are the same. So we have 1, 0, and 0, but these two numbers contributing 2 to the power of 0 are the same. And so in that case, we have 3 different numbers that could fit that 0 slot. So we actually end up with 2 choices for the number contributing a 1 and 3 choices for the number contributing a 0. And then in terms of ordering, because these are the same number, there's 3 different ways to order this. And so that's going to give us 18. And if these numbers are different, then that means to choose the exponent of 1, we're going to have 2 different numbers that could contribute that. And then for the powers of 0, we have 3 different numbers that could fit, and we need to choose 2 of those numbers. So 3 choose 2, since we're choosing 2 distinct numbers, that's going to be 3 different pairs of different numbers. 3 right here. And then in terms of ordering, because they're all different numbers, that's going to give us 6 different ways to order this. And so this is going to give us 36. And then we have our final case where the product has a power of 2 to this 2 squared. And so that means in our product, it's only going to have 2 factors of 2. And so there's lots of different ways we could divide this. So we have 2 cases. We could either have 2, 0, and 0, or we could have 1, 1, and 0. And so those are the only 2 ways we could end up with 2 factors of 2. And so if we end with 2, 0, 0, if we end up with a number that contributes 2 factors of 2, there's only one number that could do that, and that's going to be 4 right there. And so this number has to be 4, so there's only one choice for this number that contributes 2 factors of 2. If we're looking at 0 over here, we also could start splitting into cases, just like we did up here, if the numbers are the same or if they're different. And so in this case, we can almost sort of copy what we did right here, but we just have to make sure we swap out the 2's over here with 1's, because to contribute 2 factors of 2, there's only one number that could do this. So if they're the same, we're going to have one number as the 2 factors of 2, which is going to be 4. And then if they're the same, there's 3 different numbers that could contribute a factor of 0. So we pick one of those 3 numbers, and then there's 3 orderings. That's going to give us 9. And if they're different, you have one number here again. That has to be 4. And these are going to be 2 different numbers. And so again, 3 choose 2 is going to be 3. To choose a distinct pair. And then in terms of ordering, because these are different numbers, there's going to give us 6 different ways to order this, and that's going to give us 18. And then our final case is if we end up with 2 factors of 2 and they come from 1, 1, and 0. And so if we end up with 1, 1, and 0, we can also do casework on the number of ways on whether these two factors of 1 are the same. So this is going to be a lot of cases, but I think this is our last 2 sets of cases. So this should be relatively quick. All right. So if we have 1, 1, 0, if these 2 powers of 1 come from the same exact number being picked twice, that's going to be, let's see, there's 2 different numbers that could contribute a power of 1. That's going to be 2 and 6. And then for our power of 0, there's 3 different numbers that we could have contributing that power of 0. And then there's going to be 3 different orderings since they're the same number. And that's going to give us 18, I think. And then if these are different numbers, I probably should have labeled this, but if they're going to be different numbers, we have to choose 2 out of the 2 numbers that could contribute 1. And there's only one way to do this because there's only 2. So 2 choose 2 is going to be 1. One way to choose a distinct pair. To choose the factor of 0 right here, there's 3 different numbers this could come from. And so that's going to be 3. And then in terms of ordering, they're different numbers. That's going to give us 6, which is 18. Again, hopefully I didn't make a math error somewhere in there. So all we have to do now is add this up, and we divide this by 6 cubed because there's 6 cubed total different possibilities, since with each roll we have 6 different numbers. So let's see, if we add this up, adding this up, this is 54. Adding this up, this is 27. Adding this up, this is 36. This is 27. Add the two 27s to get another 54, and adding that 54 gives us 108. 108 plus 36 is going to be 144 over 216. I think we can divide both by 72. I think that goes in. That gives us 2/3. Okay, that was a long problem. Hopefully it's 2/3. And yeah, it is going to be 2/3.
Wow. Yeah, that's pretty good. That was a long problem. I will say I did see one little place that you can save some time. Only like at some point you were doing. I'll just do one example. You did pretty good stuff. But at some one example was new when you had like the 1 0 0. I think another way you can think of this, you were thinking of whether they were the same or not. But for the 1, there was either 2 or 6. So there was 2 choices. And then for each of the zeros, it's just 1, 3, or 5.
Oh, that is true. It does add up to yeah, that is a nicer way to get the sum actually.
Although I had to
That probably
check.
gonna save time.
No, I also had to think, like, while you were doing it, I was like, am I going to make a mistake? Because I saw people typing into this thing. It's so easy to get a mistake. So yours definitely didn't get a mistake. Because with the thing I was doing here, there's this slight danger of like, do I multiply by 3 at the end or multiply by 6 at the end? Yeah, but good. Well done. Yeah, people are saying they hope question 30 is easier. Since when does anyone have question 30 easier? Oh no, I got question 30. Right, what's this? I might need you guys' help, by the way. So please help in the chat. Let's see. Circle O has radius 6 centimeters. Okay. Point A lies outside circle O, and the rays with endpoint A are tangent. What a crazy diagram. Okay. Similarly, point B lies outside. I see point B. And the rays with endpoint B are also tangent. Okay, I see that. If the measure of angle CAD is EBF is 60 degrees. Okay, those are marked. And AOB is 90. That's also marked. What's the area of this quadrilateral? Huh. Okay, so the important thing is that we know something about the radius is 6. Oh, good, nice picture. So if the radius is 6, I guess I should get some distances which are 6. Like that's 6. So every time I draw a radius, that's 6. But now I guess I'm a little bit curious what kind of angles we have inside. I wonder if I can figure out any of these angles. So, well, whenever there's a line that's going from the center of the circle, I should also say, unfortunately, we're going to be out of time after this because we'll have gone past the half hour. So I think we won't get to the target round if you were wondering about that. So instead, let's just see if we can figure this out. So, right, we had 60 degrees over there. So the center of the circle going over to there cuts it in half. So that means that this is 30 and this is also 30. Could that be useful? Oh. So let's see. We got some tangencies. So whenever there's a tangent, you see, I'm just thinking of the things I can use about all of the parts of the problem. Whenever you have a tangent, when you draw the radius to the point of tangency, there's a right angle. So that's a right angle there. Aha, so now I see a 30, 60, 90 right triangle. So what do I mean? What I see is, let me go and point it out here because then I can point a little bit easier. So I see there's a 30 here, there's a 90 degrees there. And so that means that over here, this is a 60-degree angle. So that is 60. Well, if that is 60, there's some symmetry here. So if that is 60, this is also 60. So in that case, something neat's happening. I have a 90-degree angle. I have a 60 here. I have a 60 there. Well, it looks like I got 30, 60, 90 triangles everywhere because I've got 30-degree angles everywhere because if this part is 60 and the whole thing was 90, well, what's this part? That's 30. So that means that this picture right here has lots of 30-degree angles. So this is 30, this is 30, and this is 30. Okay. The next thing I need to know is, what about this? I'm again going to use the fact that whenever you have a tangent line, it's always perpendicular to the radius. Okay. Ooh, meanwhile, I can see that in our internal chat, Elena has a slightly faster way to do 29. So maybe after I do this, we'll bump back to Elena as the bonus to wrap up everything. Okay, I'm excited. See, we have a secret internal chat here, so that's a lot of fun. But in any case, I need to go and solve this problem. So if that's 90 degrees, what else can I do? Ah, right. I'm just chasing angles. Oh yeah, that's what this is called. This is called angle chasing, right? So if I've got 90 degrees here and I've got 30 degrees up there, chasing and chasing, that's 30, this is 90, so that means this is 60. Oh, cool. I guess that does look like a right angle. These are perpendicular, so that's a right angle. Okay, with that, I have now figured out a lot of the important angles. So this thing here is a right angle. This thing here is a right angle. I promise, that's a right angle. And so the part that's out here, well, the sum of all the angles around will be 90 plus 90 plus 30 plus something is 360. These two add up to 180 already. So that means these two, the 30 and the other part, also add up to 180. That's 150. Hard to read, but that's 150. Okay, so now I need to go and actually figure out the area of this. What's the easiest way to do that? I'm trying to think because I know a way to do this using a high school area formula, but that's trigonometry. So is there a way to do this without trigonometry? What if I move things around? Would that help? Yes. Yes. So I'm trying to do this in a way where I don't use this. There's an area formula, by the way. It's called 1/2 AB sine theta. I don't want to use that though. So I'm actually thinking, what if I grab this piece and just roll it around here? My hand, unfortunately, or fortunately, can't roll that well. But I want to take this piece and roll it around because I see a 30 here and I see a 150 here. And 150 plus 30 is 180. So if I take this piece and roll it around, I'm going to get a nice straight line. Is that useful? I would get this nice straight line cutting through. It's actually a diameter and cutting through like this. So here's what I'm doing. I'm saying, suppose that I rolled it all the way around, then I'd get this going all the way across to here, and then like this. So this triangle has the same area as this triangle, okay? The reason that's useful is because there's a theorem in geometry, which I think many people see in MathCounts, which is that if you take a diameter of the circle and you take any other point on the circle, then it makes a 90-degree angle with that diameter. So this is a 90-degree angle here. So if I want to go and get the area, if I want the sum of the areas of these two weird triangles, that's the same as that area, this thing here. Is that doable? Hopefully, because hopefully we know something about some angles. So if that's 150, I would like to get this angle here. I'm trying to think of the easiest way to do that. That's an ugly number. That's 75. Okay, I'm trying to think if there's a way to do this without using the 1/2 AB sine theta. At this point, I'm going to go ask my co-stars. Does anyone see a nice way to do this without using 1/2 AB sine theta? Because I didn't know that was actually part of the MathCounts curriculum. You see, I do know a formula which can solve this thing, but I would like to not use it if I can. Area is 1/2 AB sine theta. I was trying to avoid that, but this approach won't avoid that. Okay, well, what I'll say is if any of my co-stars see a way to avoid this, I'm very happy if you jump in. Otherwise, I would go on and try to do it with that formula. So, okay, well, I guess I'll go ahead and use that formula since I guess this is question number 30. So what is the sine of 30 degrees? The sine of an angle is the opposite divided by the hypotenuse. So I guess there is a way to describe this Yeah, okay. I see a way to do this without actually writing the sign thing, right? But it's the opposite over the hypotenuse. And I see how I could do it by just drawing it here. Yeah, we can do that. So let's just do this in a more basic way. The good news is that sine of 30 is nice. So I'm going to draw the ODE. So this is OD and E. And this actually proves the formula that I just wrote here. But this will be okay. So I'll have a 6 here. That's 6. If I have a 30-degree angle, if I want to know the area of that piece, let's just draw the altitude. Okay, so the altitude, do you see a nice triangle? This is a 30, this is a 90. So what's that? That's a 60. So if that's 6 there, what's the height? Well, the height's nice. The height is half of 6, which is 3. So in that case, now the base, the OE, that's 6. So I can find out that the area of this triangle is half base times height, which is 1/2 times 6 times 3. This area of that little piece is 1/2 times 6 times 3, which is equal to 9. Okay? And that's the key concept actually for the 1/2 AB sine theta. Oh, I see. Actually, the area of this long flat one is in fact the same. And the reason it's the same is because if I went and completed this piece over to here, the height of this triangle is the same as the height of that triangle. So specifically, what I mean is if I imagine trying to make the height where the height is still the blue thing, this is the height. That height is the same as that height because this angle is 30 degrees. So in fact, the area of this piece and this piece are exactly the same. Okay, so these two are the same area because they both have the same base of 6 and they're exactly the same height of 3. So I've got two areas which are 9, and the last two pieces, this 6, 6. Oh, that's cool. So the area, no, that's not. So this is 6 times 6, and I have to do times half because it's half base times height. But I won't times half because I've got two of them. So if I put these two things together, I get a nice square. All right, because this is a right angle already. So if I take that triangle and that triangle put together, I get a nice square. So if I go and add everything together, hopefully this is the right answer. Total equals, let's make the whole square, which is a 6 times 6 square, which is 36, plus we have this one which is a 9, and that one which is a 9. That's 18. I think that's 54. Yay! Okay. Right. So I guess that means that this did solve the problem, and we managed to actually prove half AB sine theta. And let's do the finale with Elena, because she says that she has a nifty way to solve.
Well, I mean, it is pretty similar to Jesse's solution, but I did want to emphasize a solution where we use just simply probabilities and where order doesn't matter. So what I've done here is I've counted up the numbers of powers of 2 to the power of 0, to the power of 1, and power of 2. And the chance of getting to the power of 0, if you just roll a die, will be 1/2, because there's 3 of them. And then for first power, you have 1/3, because there's 2. And for second power, you have 1 of them, so that's 1/6. And then we can just simply write each of these, sort of not accounting for order, or at least not accounting for what the value in each position actually is. So for example, in the case of 0, 0, 0, we know that this is 1/2 cubed, because the probability of each one is 1/2. And then for 1, 0, 0, we do actually care about the order of the 1 in between the zeros. So there's 3 ways to change that around. But then for each of the values, we don't actually care what's there. We just care that it carries the right power. So we would have 1/2 squared times 1/3. And then for the 1, 1, 0 case, we have, again, 3 ways to arrange it. 1/3 for each of the 1s, and then 1/2 for the 0. And then for the final case, we have 3 ways to arrange it. We have 1/6 for the 2, and 1/2 for each of the 3s. Or 3s, zeros. So then if we were to just do it all out and these are all successful outcomes. So what we're going to do from here is we're going to add together all of these probabilities to get our final probability. And as I'm looking at these probabilities, it seems like the common factor is going to be 24 in the denominator. So this is 1/8 or 3 over 24. In this case here, we have 3 over 12 is equal to 6 over 24. In the top right case, we can cancel out a 3. So we'll have 1 over 6 or 6 over 4 over 24. And then in this final case, we have 3 over 24. And when we add these, maybe I did a math error somewhere, question mark?
I think you're okay.
3, 6, 3. Oh, 16, never mind. I did a math error when checking for math errors. So we add them all together. We have 3 plus 3 plus 6 plus 4 in our numerator, which gives us 16, and in the denominator we have 24. So this gets us to the same answer of 2/3. The quick hack here, there's like two sort of hacks involved, which is using the probabilities directly and not really caring for what is in that place value, because they're all equivalent. They all make it work equally.
Yeah, nice. Okay, well, with that, what I'm going to say is we actually really enjoyed talking to all of you guys today. We also enjoyed doing the problems, I have to say. And I hope that you can see that these questions are really interesting. And I really hope if you live in the United States, if you're going to be in middle school next year, strong recommendation, join MathCounts. You won't regret it, because all of these questions, as you can see, they're not like normal questions that you'd see in a textbook. You actually have to go and think. And when I was learning, I actually did, oh yeah, another advice. Don't find somebody to go and teach you all of the methods by just showing you how to do the problem and practicing 10 of them. That's not what we did today. Today, what we did is we just kept looking at interesting questions and thinking about them. That's the best way to learn. Well, with that, I want to thank MathCounts for doing this official collaboration with us. As I mentioned, it's very meaningful to a lot of us, well, all of us, very meaningful to all of us, because a lot of us got our start in the MathCounts. With that, I'll say good night or good morning to you wherever you are, and we'll see you next time. Take care. Bye-bye.